I improvise.
Sure, no, I got it.
Thank you so
All right,
much.
so hey everyone. My name is Ameet. I am a faculty at CMU in the machine learning department. I was previously, I guess a while ago now, a postdoc in the AMP lab. So I have very fond memories of Berkeley and probably sat in the same place that many of you at one point sat before the pandemic and everything. But anyway, it would have been great to be back in person to visit a place I am very, very fond of. But I guess the next best thing is to try to talk to folks via Zoom. Yeah, so today I'll be talking about some of my recent research titled Algorithmic Foundations of Neural Architecture Search. I guess before we start real quick, I'm happy to take questions at any time. I don't know how people typically, should I have my Zoom chat open or are people just gonna chime in and speak? How do you guys typically do that?
So I was just typing a message in the chat. We're gonna keep the chat muted so that we don't have to look at two things. Please put all your questions in Q&A.
Oh, so okay, so I don't need the chat open. Let me get myself set up then. Oops, 1 sec. I've never used Q&A. I only use, all right, this is fine though. Okay, cool. All right, so let's see how much I can get through today. Hopefully I'll get through the whole thing. If not, no big deal. Happy to answer questions whenever. But all right, so kind of motivation for this talk, and some of this, I imagine most of this is not news to you guys, but we're evidently in the golden age of machine learning for a variety of reasons. From a research point of view, right, we have seen some amazing technical achievements and gains, right? So ImageNet, we've achieved superhuman level performance on image recognition. Leading machine learning conferences are just growing exponentially. This is a joke about the registration growth and NeurIPS registration outpacing the world population in the last, in the next 20, 30 years. It certainly is the case, even when I was at Berkeley 5-10 years ago, you didn't have to, everybody could fit in one room. It was a small conference, and now it is what it is. From kind of an industrial point of view, again, AI has sort of taken over. Google has become an AI company. We're seeing some amazing advances powered by AI, deep learning, and machine learning. From an educational point of view, similar trend, right? Berkeley has a data science program. Carnegie Mellon has the first AI program. Computer science is the major that everybody cares about. Keras for kindergartners, I don't think is a real thing, and I'm happy about that. Maybe it is these days, I don't know. But kind of these different trends all suggest that ML has already arrived and people are using it everywhere, right? I would argue, in fact, it's kind of the opposite, right? We're not really ready for widespread adoption. And again, I think I'm, to a large extent, preaching to the choir here. You folks in the RISE lab are kind of building infrastructure for machine learning with the understanding that there's a horrible lack of infrastructure and systems for machine learning existing today. But, an analogy that I like to talk about to kind of explain, my perspective on this and where I think a lot of the pain is to think about the field of aviation, say about a century ago. So this is a picture of the Wright brothers in, I think, 1903 in Kitty Hawk. It was a pretty modest event in terms of absolute terms. They flew for tens of seconds and hundreds of meters, but they showed that powered flight moved out of the realm of science fiction and into something that seemed plausible and, possible to be a real thing one day. Right? The Wright brothers and several other people worked hard over the next several years. The World's Fair was a big deal, evidently, back in the day. And they demoed their advances over those 7 years at the World's Fair, at which point, it's kind of known that powered flight became culturally accepted. It was something that throughout the world, people believed would really fundamentally change the way we lived. That said, in 1910, you had to either be fighting a war or be extremely rich to actually have any personal interaction with powered flight, right? And in fact, it took another 4 decades before the commercial jet age commenced. In the meantime, of course, planes were, heavily involved in World War I and World War II, but they weren't widely adopted, for nearly 5 decades, until nearly 5 decades after the Wright brothers' seminal pioneering flight, right? And so kind of how do we get from the pioneer age to something more like this, right? And basically we had to invent the field of aeronautical engineering. Right? We needed more efficient planes, right? Turbine engines to fly across the country, across the world. We needed automation in terms of the building and safety testing of airplanes. And kind of more generally, we need to really consider safety from the point of view of making this of widespread adoption. So the creation of the FAA, other sort of regulatory agencies as well. And so, how does this relate to machine learning? Well, I'd argue that we're in the pioneer age of machine learning right now. So the success of ImageNet in 2012 was this watershed moment. It kind of made it impossible to ignore that, wow, deep learning and machine learning more generally can do some pretty amazing things. And at this point today, you could argue that machine learning really is culturally accepted, right? But it's restricted to the Googles and the Facebooks of the world. And the question is, how do we get to this jet age of machine learning, right? And so there's a lot to do there. And I think kind of these pillars of efficiency, automation, and safety, and generally thinking of machine learning more as an engineering discipline very much holds true, for our field as much as it did for the field of aviation back in the day. And the specific topic I'm going to talk about today, I think represents one important step towards democratizing machine learning related to both efficiency and automation. So kind of the outline for my talk today. First, I'm not clear how many of you guys are, I know likely about related areas, but I want to get us first on the same page about what this neural architecture search problem is. And once we're on the same page about this background, it sets up pretty well kind of the very simple questions that my group and I have been asking for the last few years in this area. So I'll get back to the question. The questions will become much more clear after I go through the background. And I should say again, please feel free to stop at any time if you have any questions. Okay, so what is kind of the starting point for neural architecture search? Well, it's this problem of designing neural networks. So this is a picture, for instance, of GoogleNet. It won the ImageNet competition in 2014. And if you're anything like me, you look at this and it seems like, black magic. It's not at all clear to me why this architecture was designed the way it was. I would not know how to design this architecture. And in fact, the general process of designing neural networks is this really ad hoc, expensive designs process, restricted to experts. So GoogleNet, for instance, was, right, it took several deep learning experts at Google, years of effort and probably huge amounts of compute to design this sort of network. And at this point, this is, right, a 6-year-old network. Modern networks are much more complex than something like GoogleNet, right? So kind of the excitement around NOS is that it has this potential to automate and speed up this process, making something that's really opaque and seemingly impossible for all but a handful of experts to actually be possible for non-experts on new problems. So things other than, say, image recognition or kind of leading NLP tasks. Okay, so to understand NOS and to kind of introduce the problem more formally, it helps to think about it relative to hyperparameter search, which is probably a problem that you guys are all more familiar with. And at this point, I think it's pretty well established that NOS is an important subproblem of hyperparameter search, but it really is a subproblem of this broader problem. It's not a distinct problem, it's just a kind of a special instance of this broader hyperparameter search problem. Okay, so what is hyperparameter search? Right, it's the general problem tuning machine learning models. And kind of in practice, the way people typically think about hyperparameter search, especially in the context, say, of neural networks, is you start with a fixed backbone architecture, right? So something like this linear chain with a certain number of fixed layers and a particular way that the different layers are connected to each other. But then you have these knobs that you want to tune, both architectural and non-architectural parameters. So in some sense, hyperparameter search, general hyperparameter search applied to deep learning can in some sense be viewed as neural architecture search because you might mildly tune things like the number of nodes per layer, the number of layers, or the activation function. But kind of practically speaking, the distinction is that you're typically starting with this fixed backbone. And in addition to kind of minor tweaks on this fixed backbone from an architectural perspective, you're also considering non-architectural hyperparameters. So things that affect the optimization process, say like the learning rate or the batch size, as well as things that might affect generalization. So for instance, various types of regularization. And the hyperparameter search problem, which again, I think many of you in the audience are probably aware of, is a hard and expensive problem, right? And so I'm not going to go into details of this quote, but kind of it can take days to a week to train an individual model. And typically for hyperparameter search, you might want to train, hundreds or thousands or tens of thousands of models. And so for this one academic study, for instance, that we're citing here, and it really is an academic study on a pretty modest data set, it required training 10,000 models and nearly 3 decades of compute time, right? So this is a really time-consuming and expensive problem on its own. So neural architecture search kind of is attempting to solve an even harder problem, right? So if we start again at hyperparameter search here, what we're doing instead with NAS is really relaxing this fixed backbone to consider a much wider set of architectural hyperparameters or knobs to consider. So what operations to perform at each layer, and kind of the network connections themselves. It is the case that with neural architecture search, you typically don't consider non-architectural hyperparameters at all. So in that sense, the search space is slightly restricted. But overall, the search space for neural architecture search is drastically larger than traditional hyperparameter search problems. Okay, and kind of the broad goal is to kind of design these networks. Right, so that's fine, but even the problem for some toy sort of network like I'm showing here in the slide represents potentially a really large search space. But going back to the state-of-the-art networks back in even 2014, these networks are significantly more complex and significantly bigger. And the kind of upshot is that while in theory neural architecture search has this great potential, there's this promise to do something pretty amazing to abstract and automate what is currently a very opaque process. In practice, if the search space is just so comically large that you can't hopefully search over it, then it's really just an intractable problem, right? So that's kind of, the general NAS problem. And it seems kind of, there's some tractability issues here. So what have people done, or what did people do kind of starting in the first version of the NAS problems? Well, they did something which I would say is pretty clever and reasonable, which is that if you go back to this Google network, even though it's a really large network and seemingly very complex, it's built based on on the simple inception module, right? And you don't see it appear once, but you see it appear over and over and over again. And so the idea of the standard way that people do neural architecture search today is, instead of trying to learn this full network, let me focus on a restricted, let me focus my search learning this module and repeating it in some way. So these modules are called cell blocks. And kind of this is a toy picture that I'm going to be referring to repeatedly in the talk. This is a picture of a toy cell block. So here there are 4 nodes in the cell block. And basically the choices that we have during our search process is to learn the edges between these different nodes. And for each edge, we can learn what operation to perform. And again, in this toy example, we're just considering 2 possible operations on each edge, either a convolution or a pooling. In practice, these cell blocks are typically larger and there's more operations that you can consider. So the idea of NAS is typically to learn the cell block and then glue it together multiple times, similar to how Inception is kind of glued together multiple times to form GoogleNet. And so this fixed meta architecture is the final architecture that you learn, but really how the cell blocks are glued together is typically fixed, and it's really, you reduce the search problem to learning one of these cell blocks. Okay, so that's sort of the background of how the problem is motivated and how we try to get something that's potentially tractable. To be clear, these are still really large search spaces that are generally significantly larger than standard hyperparameter search spaces, but they're small enough that they're possibly tractable. Initial results were not necessarily tractable. They were tractable if you were Google and maybe nobody else. But these first generation NAS methods looked at these cell block search spaces, focused on 2 standard, but pretty common and well-studied benchmarking tasks related, one in NLP, one in Vision, the Penn Tree Bank dataset and the SFAR 10 dataset. And for both of them, they were able to achieve state-of-the-art performance. Again, they threw comical amounts of computation at these problems to the point that, again, you had to be Google to be able to potentially run these experiments. But the empirical results were really impressive. And so this really spurred a lot of excitement in this field. And it led to a flurry of new heuristics trying to optimize these 2 benchmarks. Right? And again, all I'm showing here are the papers that came, and probably a subset of the papers that came out soon soon after these first 2 papers. Since then, every NeurIPS, every ICML, you see a dozen new neural architecture search papers. So this, as soon as I made this slide, this is outdated. I don't mean to say this is in any way exhaustive, but this is kind of a handful of some of the methods that came out soon after the first initial results. There's 2 in particular that caught our attention and that I'm going to talk more about today. And these are ENOS and DARTS. And the reason they caught our attention and the reason they became pretty prominent in the field, we're due to their both performance and empirical results. So here's a running slide I'm going to show throughout the talk. These are benchmarking results on the Pentree Bank data set. We'll get back to the Safar 10 benchmark later in the talk. But the y-axis here is test perplexity. Lower is better. And this ENOS method was able, the results that they show for test perplexity were a little over 56. And there were kind of two important points that came out of it. First, they got state-of-the-art perplexity. They even outperformed the first generation NOS methods. And more remarkably, not only did they get better perplexity, they were 3 orders of magnitude faster. Granted, the initial methods were just comically expensive, but basically you went from decades of compute time to basically being able to run something overnight. 3 orders of magnitude complexity of speedups are unheard of, but it also meant that NOS was now a research field that was potentially accessible to a broader community. The DARTS paper came out soon afterwards, and again, it further improved on test perplexity, achieving state-of-the-art perplexity again. And similarly, it was, again, computationally similar to ENOS, so very, relatively speaking, quite efficient. So at this point, this is when my group started getting pretty excited about this area and kind of wanting to understand more what was going on. Our group had worked much more kind of on general hyperparameter search problems. So we were kind of coming into the NOS problem kind of as outsiders, just trying to understand the lay of the land and what was going on. And we started by asking very basic questions. And what I'm going to talk about today with our research are really kind of our exploration of these very basic questions on this NOS problem. So the first question was kind of one motivated by some skepticism, which is that, wow, random search is doing really, really badly here. And is this something that we can actually trust? Are these really the right baselines to be comparing against? Right, so a lot of our work in general hyperparameter search had been focused on speeding up random search. And we found that you could do, effectively get state-of-the-art accuracy on a wide range of benchmarks in a principled fashion by, using early stopping methods. And so we were surprised to see that random search was doing so badly here. And note here that I had to break the y-axis here to even fit random search on the y-axis because it's doing so badly here. Right, so that was kind of the first question we wanted to ask. The second question is, which algorithmic components actually mattered for neural architecture search, right? So I'm highlighting here ENOS and DARTS, which are 2 of the more prominent neural architecture search methods. But as I mentioned, these are just 2 of a wide range of methods that were introduced. And many, many more have been introduced since. And kind of, again, going back to our research on hyperparameter search, our thought is that simpler is better, right? A simpler method is easier to theoretically characterize. It's easier to make robust and build, maybe production quality systems out of. And, we really wanted to understand what was actually going on here, okay? So our first line of work really aimed to focus on these 2 questions: appropriate baselines and what components actually matter. And, armed with a better understanding for those 2 questions, that led us to ask a third question, which, the first conclusion we had is that DARTS is actually, DARTS and DARTS-like methods seem really promising and seem to be doing something interesting. And given that that's the case, we wanted to know, can we do better with simple and principled methods, right? So kind of a further investigation in terms of what DARTS is doing, why it's doing what it's doing, and with better knowledge about what's going on, can we get better results? So that's sort of the outline of what I'll be talking about today. And right, the first set of work is, all of this work is with some amazing collaborators. A lot of it is led by a student of mine who recently graduated, Liam Lee, as well as several other people listed on the slide, including some Berkeley folks. All right, I'm going to pause for a second though to see if there's any questions.
Ameet, so we had some technical difficulties, and it looks like me and Boban have both been demoted from host, and you're the sole host. Are you able to open up the panelist window in Zoom and make us both hosts again?
Man, I have a lot of power. I probably I want to do that. That's the question.
Actually, it seems like Q&A is working now, and there's already a question from Melly.
Okay, yeah. Let me fix this, and then I'll ask the question. So, what do you want me to do? I have to go to.
So open up the panelist thing, and then click on my name, like hover over my name, and you'll see a thing that says more, and there should be something there when you click on more that like make host.
Let's see. Oh, you know what? I think this maybe what I have to do. I don't see it. I see participants, and then
click that.
Okay, cool.
Yeah.
And now I need to more. and I make co-host. Boban's a co-host now. Okay, I see. And then make co-host. Perfect. So you guys are co-hosts now.
Great, thank you. And yeah, and you see you got a question in the Q&A,
Yes.
so you can just,
Sure, I'm on it. Why can't I see the Q&A though? Where is it?
It's on the bottom the button is next to participants.
Yeah, no, I see it, but when I click on it, it's not opening now.
Do you want me to read the question to you?
Yeah, but hopefully there'll be more questions. It'll be easier if I can. Just give me a second.
All right, sorry, yeah.
Oh, no worries.
This is growing pains for all of us.
Oh, I see. There is a chat here, but okay, chat's muted. It was open a second ago. Now it's just not opening for me. Let me stop sharing and see if that fixes things. And then, bizarre. Yeah, I can't seem to open the Q&A, so unfortunately, I think you might have to read to me.
Okay. I'll do that. Okay, so it says, is there a standard way? So this question is from Mele Elable. I actually don't know how to pronounce your last name. I'm sorry, Mele. Is there a standard way to evaluate the performance of an architecture relative to non-architectural hyperparameters? For example, do you evaluate performance on different architectures for fixed non-architectural hyperparameters? Or for each architecture, do you evaluate its performance over a range of non-architectural hyperparameters?
Yeah, that's a good question. Right. So I will briefly talk about this at the end of the talk, but there are multiple. Yeah, NOS typically is aiming at trying to. It's a multi-stage process, and one of the processes involves doing an offline hyperparameter search afterwards. It kind of depends on the benchmarks you're looking at, but I would argue that the right way to do it is kind of what you're suggesting, which is you do an offline hyperparameter search for whatever you pick afterwards, right? Yeah, you still want to be tuning your hyperparameters, your non-architectural hyperparameters. You typically do that separately rather than jointly with them in a separate downstream step. Okay, this is a bummer that I don't know how to. Yeah, I think I'm just going to keep going, and if there's more questions, maybe you can.
Yeah,
it's unfortunate myself, but I don't know what to do really other than clicking.
Are you able to see like the little notification with the number in it?
What? Oh, you know what? Oh, no, I got my chat open again. No, I saw that it was open before, but it's just not popping up as a. Yeah, I see that there's a little 1 there, but when I click on it,
someone suggested.
When I click on the chat. Oh, sorry again.
Someone has a question that's actually a suggestion saying it's probably in another window. Just
yeah, that is what I'm wondering. Yep, here it is. Good, I got it. But now where is it? Okay. Now I can't see it. Hold on. Give me a second. Oh, good, I got it. Okay, thanks, guys.
Terrific.
Technical difficulties have been solved. Okay, cool. Right. How good are NOS methods? Let's keep going. Okay, so I think the obvious answer here for us was there's been a rich amount of work on hyperparameter search. Some of it. Can you see my slides or no?
No, we can't see the slides.
Oh, sorry.
You need to re-share your screen.
Stop sharing screen. Okay. Thank you for that. How about
Terrific.
now? Perfect. Okay. So carrying on, the first question that we wanted to look at is how good are NOS heuristics? And for that, the kind of obvious direction for us was just apply some state-of-the-art hyperparameter search method to the NOS problem, right? NOS is a subset of hyperparameter search. There's been a lot of work on hyperparameter search, and it's kind of well known that random search is not state-of-the-art. Can we do better if we use more recent modern methods? And I'm going to very briefly kind of set some notation for hyperparameter search because I'm going to reuse this later for NOS. I expect a lot of this to be kind of background and kind of known for you guys, but just bear with me. Right, so typical hyperparameter searches, you have continuous and discrete hyperparameters that you're searching through, right? Some architectural, some non-architectural. The second ingredient to hyperparameter search is some sort of search method, random search being a natural baseline. what you do in random search is just pick different configurations from your search space, and then you evaluate each of these configurations. The default way to evaluate these configurations is by fully training the model associated with that configuration, right? You train it on your data, you evaluate it in some way, you get some score, you do this over and over again, you get different scores, you pick the best one, right? And so the hyperparameter search problem is, how can I efficiently identify high quality hyperparameters? Efficiently meaning, time or money or resources generally consumed. Quality is, I want, low error, low perplexity, and so on. Okay. As we talked about earlier, right, random search, training a single model can take days to weeks, right? So fully evaluating models using random search is really painful and really expensive when you have these large search spaces. There's a question of, can we speed up random search? Right, so I'm not gonna, right, this is work that my group and I have done over the last, say 5 years or so, has been really looking at principled early stopping methods, right? So this started with successive halving, and then hyperband, and then an asynchronous parallel version of it called ASHA. But the point is that this is a theoretically principled set of methods that kind of leverage that make connections to the multi-arm bandit problem to provably understand when these methods work and fail. And in practice, on a wide range of problems, we get state-of-the-art empirical performance, and we scale to massively parallel settings, right? And it's kind of used in a bunch of settings, including in Raytune, in my startup Determined AI, and a bunch of other places. And right, you could argue about whether ASHA is the state-of-the-art method, or there's or maybe you prefer population-based training. But the argument is that it is fair to say that something like ASHA is significantly and non-trivially better than something like random search. And so the question is, how would we apply this to something like NAS? The answer is that it's absolutely trivial to do it, right? Well, sorry, before we get there, kind of describing hyperband or ASHA in this landscape, right? We're using continuous and discrete search spaces. We're still leveraging random search. We're now just evaluating differently. Instead of fully evaluating, we're partially evaluating, right? And now if we want to apply something like hyperband or ASHA to a neural architecture search problem, it's trivial, right? It kind of just works out of the box, right? We already defined what a cell block or meta architecture search space looks like. You can sample from that search space randomly and partially evaluate each architecture and get a result, right? So there's really nothing to do. These experiments we ran, we used default settings for ASHA, no tuning of the model itself, of the search method itself, and we tried it on the Penn Tree Bank and Safari 10 data sets. And so what did we see? Well, the results were, I think, somewhat surprising, in the sense that ASHA absolutely, maybe not surprisingly, it absolutely blew random search out of the water, but you would expect that. But maybe more surprisingly is that it slightly outperformed ENOS and was only slightly worse than DARTS, given the same computational budget. And it is kind of worth saying here that ASHA or variants of ASHA existed at the time that the first neural architecture search papers came out. And so it kind of really does suggest that it's really important when doing empirically motivated studies that you use appropriate baselines, right? Because ASHA is a pretty powerful baseline here, as it beats some of the earliest methods. Right, it dominates previous baselines, comparable to ENOS. DARTS is still better, right? So this kind of motivated this next question of, what algorithm components matter? How does partial training different from full training? Right, so I'm skipping the details here, but basically the idea is that so there's a question from the audience. Partial training is basically just saying, in full training, let's say you have a search space, you sample 100 model architectures, 100 hyperparameter configurations from that search space. You can then train each of those 100 models as you would train any model, and then evaluate them on some held out data set and see which one is the best. That's the kind of default full training sort of paradigm. And it's ideally the right thing to do, but it's really expensive, because if training one model takes a week, training 100 models is going to take 2 years, right? And what you can do instead is you're making an approximation, and the idea is how to do this in a way that's kind of principled and safe. But instead of training these models independently into completion, you can view this sort of as a competition, where you start with all 100 models, train them a little bit for a few iterations, and then throw out the ones that are least promising, and keep doing that and pruning, and early stop the less promising methods. And so on average, you're partially training most of the models, and you only fully train a few of the models. And that effectively allows you, on the same budget, to consider orders of magnitude more configurations, Granted, you're getting noisy estimates of their quality, but both theoretically and empirically, it works. You can show that it works quite well. Okay, so that was kind of the first point. What algorithmic, how good are NOS heuristics? The answer, DARTS is better than ASHA, but ASHA is pretty good. What algorithmic components matter? So this is now going back to this landscape, right? We already talked about how ASHA and Hyperparameter are pretty good baselines for neural architecture search. But as you mentioned before, there were this flurry of new methods that came out after the initial NOS papers. And you can kind of think of these different neural architecture search methods as kind of just variants on the evaluation strategy or on the search method. All right, so all of them are looking at the cell block search space, but you can kind of just pick different categories, different options from the search method and evaluation method, and effectively read off different NOS methods that were published. Okay, and I'm not going to go through all of these different methods. That's not really the point. But what I do want to go back to are these two methods that seem particularly promising: ENOS and DARTS. And what they both have in common is that they rely on weight sharing for evaluation, right? And weight sharing, and I'll get more into detail about what it is in a second. It's a particularly promising technique or heuristic, both because it's incredibly cheap and because empirically it leads to really good results. At least when I first started looking at weight sharing, it wasn't at all clear to me what it was doing or why it should work, but the empirical results were pretty promising. So we wanted to study, all right, partial training seems to work well, but what happens if we do something even cheaper, but use the simplest search method possible? How well does that work? Right, so that was our second baseline. So ASHA was our first baseline, straight from hyperparameter search. Our second baseline was the simplest possible NOS method that we could think of, given the set of methods that had been introduced over the last 2 years. And so that led us to random search with weight sharing. Okay, so to understand kind of what random search with weight sharing is doing, let's go back to the cell block meta-architecture search space. And remember that we're doing some sort of random search. We need to randomly search over the search space. How do we do that? Well, remember, the search space is representing all possible architectures that, the choices that we can make are in terms of what edges we turn on, and for each of the edges that we turn on, what operation we pick, right? So we could sample edges and operations to get the following sample architecture, which I'm calling architecture 1. And if we were to do that, if we were doing this sort of full training, we're in this full training paradigm, what we would do is then, learn the optimal weights on some training data according to the appropriate loss function for that architecture, right? We can then sample a second architecture with different edges and different edge operations, and separately train the model and learn the associated weights, which I'm calling W2 here. And kind of in general, that this full training paradigm would involve training distinct weights for each architecture, right? And so the underlying objective there would be, sorry, I need to move the Q&A because I can't see. Right, there we go. Right, so the underlying objective here would be, an inner and outer minimization. In the outer minimization, we're trying to find the best architecture from this large architecture space. And the inner minimization is basically training a model, learning weights associated with each of these architectures, right? And so intuitively, it's doing what we want to be doing. We're optimizing to find the best architecture in the search space, right? We have distinct weights for each of the architectures in the search space. The problem is that it's incredibly costly, right? As an intermediate to this, what we could do is something that I'm calling, quote unquote, a shared weight setup, where it's not really, it's not really solving much of a problem, where the goal is still to optimize to find the best architecture. We're basically just rewriting this optimization to be a joint optimization over W and alpha. And so we don't explicitly need to learn weights for any of the architectures other than the optimal one. But this problem is really hard, right? We're trying to search over combinatorially large and discrete search space A, and right, the solution to this problem is the same as the previous one, and it's really hard, right? So what we do though with random search weight sharing is fundamentally solve a different problem, which is kind of a relaxation of the second problem, right? And so instead of trying to optimize to find the best architecture, what we're doing is we're optimizing to find the best average. We're optimizing weights for the average architecture. Cost-wise, this is really low, right? So basically now we really want to learn one set of shared weights, right? And we want those weights to, on average, do well across all the architectures. right? You can argue as to why this is the right thing to be doing, but it is an intuitive thing that you might want to do. And as long as it's a good enough signal for the quality of different architectures, maybe you're okay, right? And so with this sort of objective in mind, you can think about the random search with weight sharing algorithm is really simple. In the first step, we're trying to learn these shared weights. And the way we do that is by, we do this in an iterative fashion. At each iteration, we sample an architecture randomly from the search space. So we're doing, a Monte Carlo approximation of this expectation. And then we take an update. We do a mini batch update according to that architecture of our current estimate of the weights. So we're really just learning one model, but the gradient descent updates at each iteration are based on different randomly sampled architectures at each iteration. Now, the point of these shared weights is to use them to evaluate the quality of other random architectures in our search space. So once we've done the learning and learned these shared weights, we can then do the search and try to identify a good, maybe not the best, but a good architecture in the search space. And we do that by really just performing inference on maybe some held out data set using the shared weights for any random architecture. And that gives us a performance estimate of any random architecture that we want to consider with the shared weights. Right, so that's the objective and the algorithm that we're looking at. And going back to our Penn tree bank example, we ran this and the results were pretty impressive, right? So on the random search, on PTB, we actually were able to match the performance of darts. Actually, to the point that, to the best of my knowledge, I've not seen since our paper, people actually running more experiments for NOS on Penn tree bank because of an algorithm as simple and as simple and maybe naive as random search with weight sharing gets state-of-the-art accuracy. It's not clear, right? No one's been able to beat it since. All right, there's a question here. Could you please comment on how you chose to set U for the architecture space? U is uniform. We're really just random. It's random. We're uniformly at random. So you flip a coin to figure out what edges to pick, and then for each edge you flip a coin to pick what operations to pick for each of those edges. No, so we didn't make. No, we're doing the simplest thing possible. No, this is a completely uniformly at random. Another question, do the architectures being searched need to be similar or close in some way for the shared weights approach to be most effective? So intuitively, that seems like a reasonable question. And I think that's getting at a maybe deeper question of, what properties of the underlying search space, what are the properties of the underlying search space that are required for, random search with weight sharing or any method really to work? I don't have a great answer to that. I would say that on the search spaces that we're looking at, these Dart search spaces, they're actually really large. I don't think the architectures are that similar, but intuitively, that's I don't have anything to. My intuition would say that yes, that seems like the right thing. Otherwise, why would the weights work? The flip side though is you could argue that the goal of the weights here is, even if this is what we're optimizing for, if the weights end up in some local minima where they end up being a good approximation for a subset of the architectures in the architecture space, maybe that's okay. Because the goal here is not to find the best architecture, it's just to find a very high quality one. And if there's a bunch of good architectures in your search space, even if your performance estimates are really bad on most of them, if they're good on a subset of them, you're still gonna end up finding a good one. So actually, it's not clear that you necessarily need them to be similar or close, but I don't have anything formal to say about that. Could you please comment, what was the parameters of the search space, kernel size, layer, depth, width? So I would defer to the details in the paper. We used a canonical search space that was used in the Darts paper. So they have, right, so the main search space is a cell block, and I want to say that there are like maybe 8 nodes in the search space. Each architecture can have at most 2, I think in degree and out degree of 2. And I think that I want to say order 4 or 5 different operations at each edge. And I think there's different types of convolutions and so on. What does it mean to share weights across different architectures? Okay, so how do I answer that? So the idea of sharing weights across architectures is maybe best, is in this slide. There's some way of learning shared weights. which I talked about before, once I have these shared weights, they're shared in the sense that I'm evaluating any new architecture, right? So the shared weights are, if you think of the cell block as a super network, right? So imagine the super network containing all of the edges and all the possible operations for any architecture in the space that I'm looking at. The shared weights are weights for this super network. And so every time I want to now evaluate a particular network in the super network, I just use the subset of the shared weights from the super network that correspond to my particular network, and I can evaluate the quality of that network without doing any additional training. So I'm assuming that I'm using I'm using the same set of shared weights for that super network to evaluate the quality of any architecture in my search space. So that's how you use it to actually perform evaluation. How you actually learn them is what I talked about in the previous slide. Okay, we only have 10 minutes left, so I'm gonna go pretty fast here. There's a similar story the story is somewhat similar for CIFAR 10. I told you I'd come back to this. It's similar in the sense that ASHA absolutely dominates previous random search baselines and is comparable to ENOS. It's different though, in that DARTS is better than random search with weight sharing. And in fact, variants, other heuristics building on top of DARTS have also come out subsequently that further that increase the gap between random search with weight sharing and something like DARTS. And so, right, DARTS is a gradient-based optimization method, which I'll talk a little bit more about later. And kind of this motivates our last question of what are gradient-based methods doing and can we improve on them? Right, and this is also this joint work with some of my students and colleague at CMU. Right, so we talked about the optimizations that we were considering before. Right, the original objective is trying to search over this discrete and combinatorially large space. The random search with weight sharing approach is trying to optimize for a random architecture. What we're doing with gradient-based approximations is performing a different relaxation. Do we compare with other state-of-the-art work in vision like EfficientNet and MobileNet 3? So in this work, we didn't look at EfficientNet and MobileNet 3, but we have looked at, right, a lot of those are kind of, there's a subset of NOS that's focused on kind of deployment, resource constrained architectures. And I think these methods, or the architectures that you're talking about here, are kind of more focused there. They're interesting and reasonable to look at. We looked at the DART search space at the time. That was kind of the main thing people were looking at. And more recently, there's NOS Bench 101, 201, and one more that I'm blanking on. We tried with all of those. Do shared weights represent pseudo rank between architectures? Can pseudo ranks correlate with the original ranks? Right, so if you could show that the shared weights somehow preserved ranking, that would be enough, because that's all we care about here. It's not clear that they do, but I would argue you actually don't care about a full ranking. What you really care about is finding a good architecture in the search space. So as long as the ranking that with weight sharing you get ranks, let's say you have a set of K architectures that are very good. As long as one of that's a suitable outcome. As long as one of those K architectures is ranked very highly by weight sharing, I think that's okay, right? So I think a weaker condition holds for which weight sharing would still be a reasonable thing to do. Does the complexity of a data set contribute to the effectiveness of the NOS technique? I mean, it definitely contributes to the computational complexity. I think the bigger thing that contributes to the effectiveness of a NOS technique is the size of the search space. Right? So it could be the case that, a lot of the results we have similar results for ImageNet and for CIFAR 10, and you roughly see similar patterns. What you often see is different results, not necessarily for our methods, but for some of the other methods, they're maybe more or less robust on different search spaces. So I think the search spaces are kind of the key here. One thing I would say though, and this is a point I don't know if I have time to get to, but one weakness I think of all NOS work right now is that it really focuses on a set of problems where, right, ImageNet and CIFAR 10 are both computer vision tasks aimed to perform, object recognition. They're very, very similar tasks. The broad goal of NOS is really to allow people to design architectures for new problems and new domains. It is certainly the case, I guess maybe if this is what you're asking, it's a good question, in the sense that it could certainly be the case that I would be shocked if methods, the search space is designed for, for SAFAR 10 or ImageNet would work for some arbitrary problem in computational biology with non-image data. So from that point of view, yes, I don't know if it's a specific data set as much as the kind of domain of the type of data you're looking at will certainly matter in terms of how you design the search space and therefore the effectiveness of NOS. Okay, so I'm gonna go really quick here. I think I might just, given that I am almost out of time, I'm gonna kind of skip this and just kind of skip to the punchline here of the different relaxation that we perform here is one where we perform actually, I'll show this, right? Instead of basically assuming that you have exactly one fixed operation per edge, we allow a mixture of possible edges. So between edge 1 and 2, we say it could be some fraction of pooling, some fraction of convolution. And we want to learn this. We introduce theta as a parameter that we want to learn. The key point here is theta is now continuous. So we can perform gradient-based methods not just on W, but on these architecture parameters theta, which ultimately will tell us what we want in terms of what's a good architecture. Right, so the way gradient-based methods work is you first want to optimize over the shared weights, but also these architecture weights, which tell you kind of for each edge, do I prefer pooling or do I prefer convolution? You then have to perform some sort of rounding step though, because ultimately what you want to spit out from this procedure is a single architecture, right, with only some of the edges turned on and for each edge a single operation. Because of this rounding step, you want the results of your theta parameters to be sparse, right? Because the rounding step is going to be introduce less noise and less errors if the architecture parameters are sparse from the start. I'm going to skip through this all. Basically, the point here is that we're able to, by understanding that there are these explicit, but by understanding that there are explicit simplex constraints that you want to perform on these architecture parameters, we can use learning algorithms that are kind of better suited for this simplex geometry rather than vanilla gradient descent, right? So mirror descent generally is a family of optimization algorithms that includes gradient descent as one example. Another really common example is exponentiated gradient descent, which is in particular very well suited for the simplex geometry. In convex settings, you can show that it provably converges more quickly. And in non-convex settings, at least empirically, you see it often converges to a sparser solution. I know I've gone a little fast here, but the point here is that we want, we're introducing this mixer relaxation. We want that relaxation. We want the mixture weights that we're learning, which are ultimately going to tell us which architectures that we care about. We want those to be sparse if possible. And there's a new learning method which also converges faster, which is well known in the optimization community, that's much better suited for this problem. And by kind of making these observations, we're able to prove novel convergence guarantees for the gradient-based NOS objective. And kind of our algorithm is a meta algorithm that augments something like darts or PC darts. And we're able to run a bunch of empirical studies. We observe sparsity benefits, and we also observe real empirical benefits with Gaia. This is again on the Dart search space. We ran something similar with the Dart search space on the ImageNet data set. There were more recent benchmarks, for instance, NOS Bench 201, where typical weight sharing methods like darts perform really, really badly because of this rounding step. Gaia outperforms darts and every other method here. And actually it's nearly optimal. You kind of know this is a pre-computed benchmark. You know what the best result is. Gaia is getting nearly the optimal result. Similar results hold for, for other data sets in the search space. So kind of in summary, the three questions we asked were, how good are NOS heuristics? And the argument is, they're certainly doing something interesting and they're certainly worth pursuing more, but modern HB search methods provide really strong baselines. In terms of what algorithmic components matter, weight sharing, random search, and gradient-based optimization seem really promising. Can we do better? We've shown that you can certainly do better with kind of geometry-aware approaches, both in terms of provable convergence and state-of-the-art results. Just last minute or two, we're not done, right? We're just getting started with NOS. There's a lot of open questions, and I kind of view the broad set of concerns as there's at least two directions. I mean, there's more, but the two that I would think about are kind of SysML concerns related to, say, robustness, right? Can you apply new NOS methods on new problems? And I think this is the question that someone asked earlier. And not all methods are necessarily that robust. And there's a real reproducibility crisis here. This was part of the early paper we wrote that it's really hard to reproduce, previous results, just in terms of keeping track of randomness, keeping track of what software you use, what code you use, checkpointing results, what non-architectural hyperparameters were used. There's this other point, and folks asked about this earlier as well, is that NAS, whether it's in research and especially in production, is not something you do in isolation, right? You might run NAS to find a good architecture. You then are going to perform a hyperparameter search to tune non-architectural parameters. You then probably are going to fully train your model, possibly in a distributed fashion, on much more data once you have that architecture. Right, so we certainly haven't solved NAS. There's a bunch of SysML concerns related to robustness, reproducibility, complex workflows. As a very quick shout out to my startup, these are some of the set of problems that we're considering in the context of determined AI. A second set of concerns is this question of, are these search spaces rich enough, right? We're considering hand-picked operations, things like convolutions and pooling, which are known to work well for images, but they really rely on expert and domain knowledge, and it's not clear that they would actually transfer well to new problems. And that's really what we want. We want to use NAS on new problems, not, it's much less interesting in my mind to get, epsilon better results in computer vision tasks. Or in well-studied computer vision tasks. I want to be applying this stuff on new tasks. So there's more work to kind of trade off between the generality of these search spaces and in terms of computational efficiency and the ability to actually use them on new problems. All right, so with that, I'll stop. You can check out all of this work that I talked about today. There's paper, blog posts about them on my website. You're interested in learning more about determined AI. It's an open source platform for deep learning training. You can check it out on at GitHub. And just again, a last shout out to all my great collaborators, but especially my two students who led a lot of this work, Liam Lee and Misha Koda. Okay, cool. Thank you guys for listening, and happy to answer any other questions you might have.
Thank you very much, Ameet. Yeah, so if anyone has any questions, go ahead and type them into the Q&A box.